In this video, we are going to be talking about transformations of functions. So in this section, we'll be looking at vertical and horizontal shifts of functions, reflections, stretches, compressions, and combinations of all these transformations. So the first thing we are going to talk about is a vertical shift. So given a function f of x, a new function g of x, which is just going to equal f of x plus k, where k is just some constant, is going to be a vertical shift of the function. And if k is greater than 0, the graph is shifted up by k units, and if k is less than 0, the graph is shifted down. So below we have some examples of some vertical shifts. Let's say that the graph in solid blue here, let's call that f of x. So the dashed graph is going to be f of x plus 5, right? Because it's just the graph of f shifted up 5 units vertically. So this is going to be f of x plus 5. And the graph in dashed red is going to be a vertical shift of the graph of f by 5 units downwards. So it's going to be equal to f of x minus 5. All right. So that's vertical shifts. Next, let's talk about horizontal shifts. So given a function f of x, a new function g of x, which is going to equal here f of x minus k, all in parentheses, where again k is a constant, is a horizontal shift of the function f of x. And note that if k is greater than 0, the graph is going to be shifted to the right, and if k is less than 0, the graph is shifted left. So we have, again, a figure below showing us examples of the different horizontal shifts. So let's call the graph that's in solid blue here f of x once again. So then the graph in dashed blue, well, since it is just the graph of f shifted 5 units to the right, well, it is going to be equal to f of x minus 5. And then the graph in dashed red, since it is a horizontal shift of the graph of f by 5 units to the left, it is going to be equal to f of x minus a negative 5, which is the same as f of x plus 5. So let's just write that instead. Okay. So those are examples of the different horizontal shifts that we could have. All right. Now let's talk about reflections. So given a function f of x, a new function g of x equals minus f of x is a vertical reflection of f of x, or a reflection about the x-axis. And the reason this is because, well, if we take f of x and we just throw a minus sign out in front of it, all we are doing is changing all the the sign of all the y values on the graph of f. And so we are essentially just reflecting the graph over the x-axis by doing that. Okay? And also, so for the other type of reflection, so again, given a function f of x, a new function g of x equals to f of minus x now is going to be a horizontal reflection of f of x, or a reflection about the y-axis. And then another important thing to know here is that if f of x is equal to f of minus x for every x, then we say f is an even function. And if f of x is equal to minus f of minus x for every x, then we say f is an odd function. In other words, if minus f of x is equal to f of minus x, then f is an odd function. Okay, and we have some examples of the two different kinds of reflections here. So again, we are going to call the graph in solid blue. That's going to be our f of x. And then the dashed graphs are going to represent our reflections here, since that's the transformation we're talking about. So if we look at the graph in dashed blue, right, it is just a reflection of the graph of f about the x-axis. So the graph in dashed blue is going to represent minus f of x. So this one's minus f of x. How about I write that down here? And then the graph in dashed red, well, since it is a reflection of the graph of f about the y-axis now, it is going to be a horizontal reflection. So it is going to be f of minus x. Okay. So that's it for reflections. And we just have two more kinds of transformations to talk about. So the next kind is going to be the vertical stretches or compressions. So given a function f of x, a new function g of x equals to a times f of x, where a is a constant, is a vertical stretch or compression of f of x. And if a is greater than 1, the graph will be stretched. And if a is between 0 and 1, the graph will be compressed. And so once again, we have some examples below. So here, once again, in the dark blue, we could consider that our graph of f. So it's going to be the graph in dark blue here. I'm going to go over it with the laser pointer, kind of. That's our f of x. And then the graph in dashed blue here, well, we could think about this as being a times f of x, where a is greater than 1, because we have that this graph is just the graph of f, but vertically stretched. And then we could say that the graph in dashed red, well, it is going to be a times f of x, except now a is going to be less than 1 because we have a vertical compression. And I should say a is going to be less than 1. It's going to be between 0 and 1. So less than 1, but greater than 0. Of course, we don't really talk about negative values of a here because that's already covered by the vertical reflections. Okay. And then one more kind of transformation. So that's going to be the horizontal stretches or compressions. So given a function f of x, a new function g of x equals f of b times x, where b is a constant, is a horizontal stretch or compression of f of x. And if b is greater than 1, the graph will be compressed. And if b is strictly between 0 and 1, the graph will be stretched. And in either case, it's going to be by a factor of 1 over b. So if b is between 0 and 1, well, then say b could be 1/2. So stretching by a factor of 1 over b, well, since b is 1/2, that would be 1 over 1/2, which is the same as 2. So it would be like stretching it out by a factor of 2. Okay. And so here, once again, we have an example for the horizontal stretch or compressions. So let's call the graph in solid blue here our original function before the transformations, just f of x. Let me change the color. So this is f of x. And then the graph in dashed blue, well, since that is going to be a horizontal compression, this is going to be the graph of f of b times x for some b that is greater than 1. So And I guess I'll put b greater than 1. And yeah, we can actually see the value of b here. So b is going to be, so if we look, the graph of f here is essentially being compressed by a factor of 1/2. So that means that b is 2 here. So this would be like f of 2x. And then the graph in the dashed red, well, that is going to be our horizontal stretch. And so here, b is going to be strictly between 0 and 1. Again, since the graph in dashed red is just the graph of f stretched out. And so we can actually see what the stretch factor should be here. So here's our graph of f. And this is x equals 2 over here. And this is the same point on the transformation function, essentially. And that's going to be at x equals 4. So it looks like that now we've stretched the graph by a factor of 2. And so that means that this is going to be equal to f of 1/2 x. All right. And let's get into our one example. After we look at this example, we will look at 2 of the problems from the section 1.5 homework. So we do have some extra examples after this one. And that's mostly just to help everyone who's kind of new to the graphing utility in Lumen, to help everyone kind of understand how to go about doing those problems. Yeah. But for now, so for our example, we are given the graph of f of x equals x cubed minus 4x below, and we are asked to graph minus 1/2 f of x plus 1. So that's one transformation, as well as f of 2 times x and then plus 1. So that's our other transformation. All right, so to sketch the graphs of our transformation functions here, what we are going to do is just focus on plotting a few points that each of the transformation functions will pass through, and just connecting those points in a smooth fashion. So to see which points we are going to focus on, well, let's first start with the graph of f. So we're going to look at how the transformation is going to affect these 5 points here. So we have this point here at -2, 0. We have this point here at -1, 3. We have this point here at 0, 0. We have this point here at 1, -3, and this point here at 2, 0. So first, looking at the transformation minus 1/2 times f of x plus 1. So let me, I suppose, underline this in purple, because we're going to graph this one in purple. So just reading off the formula for the transformation here, right? So we are going to have a vertical reflection because we have this minus sign outside of the function here. And we are going to have a vertical compression as well, because we have that 1/2 out in front of the function there. And then we are going to have a horizontal shift by 1 unit to the left, because we have plus 1 inside the parentheses here for f. So we have f of x plus 1. So that means we are going to have a horizontal shift 1 unit to the left. So we are basically going to want to take each of these points from the graph of f. We are going to want to reflect them about the x-axis, And then we are going to want to shrink their values down by a factor of 1/2 and then translate them all 1 unit to the left. So if we reflect, for instance, this point here at -1, 3 about the x-axis, well, it's just going to move it to -1, -3. So we're going to be kind of down here now. But then after we take into consideration the vertical compression, we are going to shrink that -3 to a -1/2. And then we are going to want to shift everything 1 unit to the left. So that's where this point is going to go after the transformation. We go from here over to here. And then for this other point at 1, 3, so again, it's going to be reflected about the x-axis. So 1, -3. So it's going to be shifted about the x-axis. So we're going to go up here to 1, 3. And then since we have the vertical compression, we're going to go down to 1, 1.5 or 1, 3/2. And then we are going to want to horizontally shift 1 unit to the left. So we're going to be like right here at 0, 1.5 or 0, 3/2. And then for these 3 other points, well, their value is 0. So the vertical reflection won't really change anything, and neither will the vertical compression. But the horizontal shift will make all these zeros shift, well, 1 unit to the left. So that 0 is going to go there. This 0 is going to go here. And this 0 is going to go here. All right. And so now we have our 5 points plotted for the transformation function. So let's just try to connect those guys in a smooth fashion. All right. Yeah, how about we give this guy a name too? It's called the first transformation h of x. Right. So that's the graph of h. And then for the other transformation, well, we are going to do the same thing essentially. Except now we're going to graph in pink or magenta. And let's call this transformation g of x. So I'll wait until we've graphed g of x to go ahead and label the functions. Okay. So again, just doing what we did before, except for the transformation g of x equals f of 2 times x, all in parentheses, and then plus 1. So looking at g of x here, well, we are going to have a horizontal compression by a factor of 1/2, and then we are going to vertically shift by 1 unit upwards because we have that plus 1 there. So we are going to essentially want to take all these points on the graph of f, and we are going to want to bring them in by a factor of 1/2 towards the y-axis, and then shift them up 1 unit. So this point here at -1, 3 is going to move to -1/2, 3, because that's like compressing it horizontally by a factor of 1/2. And then we're going to shift it up 1 unit, so we will be at -1/2, 4 now. And then this point down here at 1, -3, so it is going to get horizontally compressed to 1/2, 3, and then we are going to want to vertically shift it up 1 unit, so we're going to be up here at 1/2, -2. And then for the zeros, well, they are going to all get compressed by a factor of 1/2 towards the y-axis. So this point here at the origin, I mean, it can't get compressed towards the y-axis anymore because we're already on the y-axis there. But this point here at -2, 0, so taking into consideration the horizontal compression, it's going to move to -1, 0. And then taking into consideration the vertical shift, we're going to go up a unit. So we're going to be here at -1, 1. And then, so again, the point at the origin. So the horizontal shift doesn't really affect this point in any way, or the horizontal compression doesn't affect this point in any way, but the vertical shift will move it up by 1 unit. And then lastly, so this point here at 2, 0 is going to get compressed by a factor of 1/2. So we are going to move it to 1, 0, and then we are going to, taking into account the vertical shift, move it up 1 unit. So we're going to be right there. And then now we have our 5 points plotted. So let's go ahead and connect them in a smooth fashion, just like before. And that's our graph of g of x. So now I'll go ahead and label these guys. So that's g of x. This was f of x. And then in purple, we had h of x. All right, so we are looking at some of the questions from the section 1.5 homework on the transformation of functions. So in this homework, you are going to have to use the drawing or graphing utility in Lumen. And so the first thing you want to do is check what kind of function you have to determine which kind of graphing utility you want to use. So in question 10 here, we are given f of x equals minus, and then parentheses x plus 2 squared, and then minus 2. So we are trying to graph some transformation of the standard quadratic function, so we're going to pick the quadratic graphing utility. And with every one of these graphing utilities, all we have to do is just plot 2 points that our graph will pass through, and then Lumen will do the rest. So as long as we just correctly plot 2 points, Lumen will do everything else for us. And so for this particular problem, kind of the easiest points to go ahead and plot are going to be, well, we want to consider when the expression in the parentheses here is going to be 0. And so that's going to be when x is equal to -2. So we would have -2 plus 2, that's going to be 0, and then that gets squared, which is still going to be 0, and then throwing a minus sign out in front of 0 doesn't change anything either. That's still going to be 0, so we essentially have f of -2 equals 0 minus 2, which is equal to just -2. So f of -2 is equal to -2. So let's go ahead and plot a point at -2, -2, because our function f is going to pass through it. And then let's try to make the expression in the parentheses here equal to a positive 1. And so that's going to happen when x is equal to -1, because we'll have -1 plus 2 in the parentheses, which is a positive 1. Then that gets squared. And of course, positive 1 squared is just 1. Then we have the minus sign out in front. So that's going to be -1. And then -2 is going to be -3 in total. So f of -1 is going to equal -3. So that's going to be right here. And of course, this is exactly what we should expect to see. So this is just a translation. Whoa. Let me resume. All right. Get back to question 10 if it'll let us. All right. Okay, we still have the same version of the question. Okay, so we had our point here at -2, -2. And then we had our point here at -1, -3. So And if we think about it, this is exactly what our graph should look like here, because we have a horizontal shift by a -2 units and a vertical shift or translation by a -2 units. So we've shifted the standard quadratic function to the left 2 units and down 2 units. So that's kind of our initial point here, -2, -2. And then we have a reflection about the x-axis. And so this is why our parabola is facing downwards. So that's exactly what we have in our graph. But of course, all we did was we plotted those 2 points. So let's submit, and yes, we are correct. All right, let's also look at question number 11, because this one involves the square root function. So here we are trying to graph f of x equals minus and then square root of x plus 3 minus 3. And so since we are dealing with a square root function here, let's pick the square root graphing utility or drawing utility. And then let's first think about trying to make the expression under the square root equal to 0. And that's going to happen when x is equal to -3. So we're going to have -3 plus 3 under the square root, which is going to be 0. Square root of 0 is 0. And we have the minus out in front. So -0 is still just 0. So we have 0 minus 3, which is equal to -3. So in other words, f of -3 is going to be equal to -3. So that's going to be this point over here. All right. And then now let's try to make the expression under the square root equal to a +1. So that's going to occur when f of x, or rather when x is equal to -2, because we will have -2 plus 3 under the square root is a +1. Square root of +1 is going to be 1. So we have -1 minus 3 is going to be a -4. So f of -2 here is going to be equal to -4. So that's going to be this point right here. And of course, if we stop and think about it, so what we're looking at here with f of x is it is just a translation of the standard square root function by 3 units to the left and 3 units down. So that's why our initial point here is -3, -3. And then it's also, once again, a reflection about the x-axis. And so that's why we kind of have a square root function that's going downwards or oriented downwards. And so let's go ahead and submit this. And once again, we're correct. So that's how you do the problems on the 1.5 homework, at least as far as the ones where you have to graph. So